In progress.
So, good evening. So, today we'll be considering some interesting network theorems. So, these network theorems will be useful to solve the assignment problems, and we will go through the network theorems. We will try to understand the proofs and all so that we can understand how they've been proved. And once we have understood the proofs, once we have understood their theorems, then we will proceed in solving the previous year assignment questions, and if any doubts are there, we can look into it. So this session is doubt clearing and problem solving session for network analysis NPTEL course, which was taught by Tapaskumar Bhattacharya from the Electrical Engineering Department of IIT Kharagpur. And so these are some notes which he has provided, which I'll be referring to while teaching these network theorems. So at the start, we will study the substitution theorem, and we will use the substitution theorem to and the superposition theorem, etc., to prove the Thevenin theorem, Norton's theorem, etc. We will also consider compensation theorem, which is basically in case there is any change in a circuit parameter while the remaining components, while the remaining sources of the network do not change, then this compensation theorem can help us to, it gives us a simplified circuit which we can use to solve the problem, to find out the change which happens in this circuit because of the change in the parameters. Similarly, there's a Tellegen theorem which is useful for two-port networks, solving two-port networks, etc. As well as there's a theory of reciprocity which we will consider. So now we have till now in this course we have learned the mesh analysis, nodal analysis, and they can be used to solve any circuit as a whole by suitably forming the writing the KVL equations and KCL equations, etc. However, in certain cases, we just want to determine the current through a particular resistor or through a particular capacitor, etc., or through a particular element. And we need to find a simplified way to, we do not need to find a solution for the current through each of the branches or the voltage through each of the voltage at each of the nodes. We just want it for a particular node or the current through a particular element. And in this case, the Thevenin's or Norton's theorem are suitable for solving it. So the complex network can be simplified into a simplified network, which we can use to determine the current or the voltage using Thevenin's theorem or Norton's theorem. And we will consider how to prove the Thevenin's theorem and Norton's theorem. The proof also will be shown, so we can verify the fact that there's a suitable method to do that. So many times so Gokul, is the screen visible enough?
Visible, sir. Yes, sir.
Okay. So today we will consider some various network theorems, and then we will solve the assignment 7 of the previous year's NPTEL session. So we'll consider. So there are a number of network theorems which we will go through today. One is the substitution theorem. So do you know what is the substitution theorem? Gokul? Any idea of the substitution theorem?
Yes, sir.
So can you give a brief description of it?
Superposition theorem, sir. Substitution theorem is all.
Substitution theorem is?
Superposition theorem.
No, it is something different. Okay, we will go through it. Okay, there's something known as substitution theorem, where like the resistor or some particular element is replaced by a voltage source or a current source, etc. So we will go through that. That is substitution theorem. Then, what is Norton's theorem? How will you describe Norton's theorem? You have been taught this, right? Norton's theorem and Thevenin's theorem. Okay, we'll consider Norton's theorem, Thevenin's theorem. So basically, Norton's theorem and Thevenin's theorem are useful when we are interested only in the current or voltage at a particular node or to a particular element, and we do not want to solve the entire circuit. We do not need to know the current through each of the elements, or we do not need to find the voltage at each of the nodes. That is not what we desire. We just want to find the current through a particular element or the voltage across a particular node. That is all we want to do. So instead of solving the entire circuit, there are two steps which we have to follow, and that will simplify our analysis, and it will help us to find what we want. So Thevenin's. So we will also consider the proof of Norton's theorem and Thevenin's theorem today. Okay. Then there is something known as a compensation theorem. So basically, compensation theorem is for whenever there is a change in the value of a particular element, etc. It helps us to form a simplified circuit, which will help us to determine what would be the change. Like what would be the change in the current, what would be the change in the voltage when there's a change in the resistance, like the resistance increases or decreases, etc. So that's why compensation theorem is useful. Then we will also study some Tellegen's theorem and reciprocity theorem, etc. So there we will first see these theorems. So my screen is visible, right? So yes. So let us consider this circuit figure 1A. Okay. There are two voltage sources, E1, E2. They are the independent voltage sources which are generating voltage across them. Like you can consider them to be batteries. And we have passive elements which are resistors, R1, R2, R3, R4, R5, and R6. Okay. So these are the various elements which are present. Now, we have come to the week 7 already, and you guys would have done further also. So we can apply KVL, we can apply KCL, etc. And we can determine the currents, we can solve X. That all we can do. But now, we know that the voltage drop across BC is I4 into R4. The voltage drop from across the terminal B to C is I4 into R4. So what we can do is we can replace this resistor by another voltage source whose value is R4 into I4. And there's a current I4 which is flowing through this battery, So this is what we can consider. So now, if we apply KVL to this network, or if we apply KVL to this network, we will still get the same KVL expression, same KCL expressions, and so the values of the current, etc., voltages will not change. So in this manner, we have substituted this resistor by a voltage source, and we can solve the circuit and we can simplify it further. So Gokul, what happened to you?
Sir, due to poor network, sir, for me, sir.
Okay.
Network problem, sir.
Okay, fine. So I was just telling like how this resistor has been replaced by a battery with voltage R4 into I4, and the current through it remains same I4. So if we apply KVL or KCL to this branch, it will come as the same as for this network. Similarly, we can replace this resistor by a current source which of magnitude I4, okay, across this terminal BC, and the voltage across it should be I4 into R4. And again, if we apply KCL and KVL, we will still get the same equations. And so what we have done effectively is there was a resistor. We can replace that resistor by a voltage source, or we can replace that resistor by a current source. But that should be a suitable value of voltage. It should be R4 into I4 as well as the current source of current I4. Okay. Now this can be possible to other elements also. Other elements of the circuit also we can replace, and we can suitably apply this to establish various theorems such as the Thevenin's theorem. Okay, now we will consider the proof of Thevenin's theorem, which is shown over here. So, is this visible?
Visible, sir. Yes, sir.
So we have a network over here. So we have this network. We will just consider it as a network. It has some voltage sources V1, V2. It has some current sources I1, I2. These are independent current sources, independent voltage sources. All right. And there are some other impedances also. Impedances means it could be resistors, capacitors, inductors, etc. are present. And there is an impedance Z over here. There's an impedance Z over here across nodes A and B. And what we want to do is we want to find the VAB. All right. So what we do is, as we just studied substitution theorem, this impedance Z is replaced by a current source. So there's a current I which was flowing through this element Z. So we replace that element, the impedance Z, by this current source I. Okay. Now once we have replaced it by a current source I, so why we are doing this? Because we want to find the voltage VAB. Now we have two options. So what we do is we can apply superposition theorem. So can one of you tell what is superposition theorem? What do you do in superposition theorem?
Sir, it consists of two sources, sir.
Now,
Two sources are more than two sources, sir.
okay.
Voltage source and current source, sir. First, consider one source, sir, like voltage source. Current source means it open, sir. Voltage source means it acted a short circuit, sir. Then we will find the current when voltage source is present, then again the current source is another current source is present. What will the current? When we add up the total current, it will be the superposition theorem. Okay. Yeah, it's correct. So what effectively is like this? Suppose this network we want to find a current I4. All right. If we apply superposition theorem, what we do, we short E2, one of the voltage sources, we short E2, suppose, and we keep only E1 in the network, and then we see what is the current flowing I4. Then what we do is we short E1 and keep E2 in the network, and we will see the current I4 which is flowing. Then the effective current I4 which is there when both E1 and E2 are present in the network is the sum of those previous two currents which we found. Okay. So that is the concept of superposition theorem. So in that similar manner, what they have done is this impedance Z they have replaced by a current source I. So, and there are these voltage sources and these independent current sources. In the first case, what they have done, they have open circuited this current source, and all other voltage sources, all other current sources are connected. They are operating. So when all other voltage sources, all other current sources are operating, they will find the voltage which comes across the terminals A, B. Okay, they will find the voltage which comes across the terminal AB. That voltage, they will call this as a Thevenin voltage. Just write it down. The open circuit voltage known as a Thevenin. Okay. So first what they have done, they have open circuited this current source and they have found the voltage VAB. Then what do? They will short these. Now only this current source is kept and the others are replaced. These voltage sources are replaced by short circuit
these current sources are replaced by open circuit. All right, and what is left in the network is just an impedance Z. It's just some impedance Z. So what effectively happens is it becomes like this. The circuit becomes like this. There's a certain Z Thevenin, and this is the current source I, and this is the terminal A, and this is the terminal B. So when only the current source is there, this terminal, this VAB will become equal to minus I into ZTH. Can you understand that? Why VAB is equal to minus I into ZTH?
How, sir? Minus.
Okay. So this is plus, this is minus. Okay. This is VAB. Alright. So we apply KVL. Okay. Current is flowing in this direction, I. So when we go from here to here, it will be minus VAB. And then we go from positive to negative. Like the current is going in this direction. And we are also going in the same direction. So that will be equal to into minus I into ZTH is equal to 0. Therefore, VAB is equal to minus I into ZTH. Does this make sense?
Okay, sir. Okay, sir.
Okay. So now when we apply superposition theorem, what will happen? The voltage VAB will be equal to VTH plus of this voltage minus I into ZTH. So the effective voltage VAB, which will be there in the original circuit, will be equal to V Thevenin minus I into ZTH. Okay, but in the original circuit, this was not a current. It was not a current source I. It was actually an impedance Z which had carried a current I through it. So it will be I into Z is equal to V Thevenin minus I into Z Thevenin. So when we simplify this, we will get I is equal to V Thevenin divided by Z plus Z Thevenin. Okay. So this actually is the what you say Thevenin theorem, and that we represent it like this. We have V Thevenin over here, Z Thevenin over here, and we have Z. And we have to find the current. Okay. So if you remember earlier when we studied the Thevenin theorem, what you did, you will first find the open circuit voltage across the element, that is V Thevenin. Then what you would do, you will find the impedance across AB. And that time you would short the voltage sources and you would open the current sources. That's what we have done. So that is how we have proved Thevenin's theorem. All right. Okay. So Google, so have you understood the proof for Thevenin's theorem?
Yes, sir. Yes, sir.
Okay. So similarly, we can also prove Norton's equivalent theorem, Norton's theorem also we can prove it like that. Same, what they do, they follow the same procedure. They find the short circuit current, they find the voltage, etc. And they do. So we will not go into that. We will directly go to compensation theorem. Okay. So let us consider this voltage source. Okay. There's this network. Okay, this is the same network which we are always considering. voltage sources, current source, and Z, impedance Z. This is a generalized network. So there's this element Z and there is some current I flowing through it. Now suppose every other element remains the same in the network. All these voltage sources, all these current sources, all of them remain the same. Nothing changes. Except what happens? This impedance increases. By some Z changes to Z plus delta Z. There's some factor delta Z, whether it's positive or negative, we don't know. And that results in a change in the current. Current goes from I to I plus delta I. So now this is a problem. So what one approach we can do is, we can again solve the entire circuit by replacing Z by Z plus delta Z, and we can find a new current I plus delta I we can find. That is one approach, but that approach will take time. So is there a shortcut or a simplified method for us to be able to solve such a problem? We will consider that. So now in this new network, there's I plus delta I flowing and Z plus delta Z. So what we can do is, we can replace this impedance Z plus delta Z by I plus delta I into Z plus delta Z. Correct? This impedance is replaced by a voltage source I plus delta I into Z plus delta Z. Uh, so there was Z over here, which was carrying current I, and there was some sort of network. What has happened is, now Z has become plus delta Z, I has become I plus delta I, some change. So this Z plus delta Z, we replace it by a voltage source, which is I plus delta I into Z plus delta Z. Okay. So what we will do, we will expand this I plus delta I into Z plus delta Z. That will be I into Z plus delta I into Z plus delta Z plus I into delta Z. Okay. This is how we have replaced this I plus delta I into Z plus delta Z. This element we have replaced by this voltage source, and then we further simplify it into IZ plus delta I into Z plus delta Z plus I into delta Z. All right. So now we will write this voltage source in terms of three voltage sources. We will write it like this. Some network. The same network, only it is replaced by this voltage source IZ, then this voltage source delta I into Z plus delta Z into another voltage source plus minus I into delta Z. Okay. Is there any doubt till this?
No, sir.
Okay. And what is the current flowing? Current flowing is I plus delta I. All right. So now, like how we have proved Thevenin's theorem, we will apply a similar strategy to prove this theorem as well. What we will do is, we will consider this voltage source plus the remaining voltage sources in the network to be active, and these voltage sources are short circuited. If that is the case, what will happen? Like, it will just be all the previous network, same thing, just this voltage source plus minus I into Z. Okay. What we have done, we have just shorted these voltage sources. In that case, what will be the current flowing over here? What will be the current? So the entire network remains the same. Just this is plus minus IZ. So it is effectively, it is just this. The current which will be flowing is I. Because it was the previous network only. It was just the original network. Before there was any change in the impedance, this was the original network. And the current which was flowing is I. Alright. So that was the previous network. Now, this is I. Now in superposition theorem, now we will short this voltage source as well as the other voltage sources in the network are shorted and the current sources are made open circuit. And the new circuit will be like this. Okay, it will be like this here with plus minus delta I into Z plus delta Z into plus minus I into delta Z over here. And the current which will be flowing is delta I. And in this case, all the voltage sources are shorted, which are there in the network, and all the current sources are left open, which are there in the network. Any doubts in this? I think it is a bit difficult to understand. So if you have any doubts, you can ask.
Sir, in which question we are doing?
We have not yet gone to the questions. We are just studying some theory. This is the
Okay,
proof of
sir.
compensation theorem. Do you know that?
Yes, sir, I know, but I have some confusion.
In compensation theorem.
Yes, sir.
Okay. All right. So can you see the screen now?
Yes, sir, I can see.
Okay. So just consider this this network is there. All right. There are two voltage sources, two independent current sources, and there's an impedance Z. Any doubt till here? Then this impedance Z has been increased by a factor delta Z, Z plus delta Z. So and all the other parts of the network remain the same. So the current changes to I plus delta I. Okay. Then we apply substitution theorem. Do you know what is substitution theorem?
Substitute.
Substitute what?
Sir, you can speak. I remember.
Acha, if I tell you, you will remember. Okay.
Yeah.
So, so this impedance Z plus delta Z is replaced by a voltage source plus minus the current which is flowing I plus delta I into the impedance which is Z plus delta Z. Okay. Here they have not printed it properly. So it is effectively like this. I plus delta I into Z plus delta Z. And then we have opened the brackets and we have found it to be like this. So they have also done that. What they have done is this voltage source, now they have written in the form of three other voltage sources. The current is I plus delta I. This is one voltage source IZ, another voltage source delta I into Z plus delta Z, another voltage source of plus minus I into delta Z. So till here, is there any confusion?
We can write in three voltage source of one voltage source.
Yeah, this one voltage source has been it's been changed, like it's been divided into three voltage sources. Okay.
Okay, sir. Okay.
Into three voltage sources. So now
Okay.
they apply superposition theorem. What they do is they will short these two voltage sources and they will consider all other sources to be active. Okay, they will just short these two voltage sources and all other sources are active. So the effective network will come like this. These two sources are shorted and there's this voltage source plus minus IZ. Okay.
Mm-hmm.
And if you see, this was actually the original network where the impedance is Z and the current was flowing is I.
Yes, sir.
Yeah. So whatever was the change has been ignored. Okay. Whatever was the change has been ignored and it's just the same original network. And also all these other sources are active. Now we are still continuing to apply superposition theorem. So what we will do is here these voltage sources and these current sources are replaced, as well as this voltage source is replaced by a short circuit. All right. So the effective network comes to be of this form. Where the voltage source is replaced by a short circuit, current source is replaced by open circuit, and the impedance is and Z plus delta Z and I into delta Z. Any confusion here?
Mm-hmm. But sir, in first case, we are considered these sources like V1, V2, and I1, I2.
Yeah. But in
But
next
in
case,
this case,
tell.
but in this case, we are removing.
Yeah.
Why?
See, what is superposition theorem? Superposition theorem states that, like, let us consider this network, okay? This network over here. Consider this network over here. We want to find the current I4, okay? We want to find the current I4. What we do, we replace this EMF, this voltage source E2 by 0, short it, and we will find the current due to this voltage source alone. We will find the current I4 due to this voltage source alone. That will be some I41. Assume that. Okay. Then the next step, we short this voltage source, and this voltage source will be active, and we will get another current I42. Okay. Then the actual
Yes, sir,
current
then-
flowing to the original network is I41 plus I42.
Yes, sir. Yes, sir.
So here there were individual voltage sources which we replaced. But in this case, what we are doing is we are clubbing the voltage sources and current source. In one case, these all voltage sources, current sources, sorry, I didn't go. In this case, these voltage sources and these current sources, as well as this voltage source are active. And we see the effective current I, which is flowing through this terminal between A and B. Okay, that is the current I. Then these voltage sources are replaced by short circuit, these current sources are replaced by open circuit, and these other two voltage sources are considered in the network. And so that then the current which will flow will actually have to be delta I. Because the original current was what? The original current was I plus delta I. The original current was I plus delta I. So if this current is I, this current has to be delta I.
Okay, sir.
Yeah. So that's just the proof of this compensation theorem. And we will be using it to solve one sum. All right. So, have you been taught graphs in networks?
Graph theory?
Graph theory for networks?
Week 8, sir. Week 8.
So, week?
8. Week 8 is the graph theory, sir.
Okay. Okay. So just some brief thing of graph theory, like there's an element, voltage across it is Vn, current is In. For some nth element. Okay. So for element 1, it is plus minus V1 and current is I1. And they have considered direction of the current to be from the positive terminal to the negative terminal. So that is what we have considered. Now, see, this is a network. Okay, this is a network. So what happens between two nodes? We connect it by an edge, and the voltage across it is plus minus something, and the current flows through it. So like this is one graph. This is a graph of this network A. Any doubts in this?
No, sir.
No.
No.
But sir, in case of network graph theory, B will open circuit of a current source, right?
That comes in a later part. Okay. We'll consider that later. This is just a simplified format. Right. Next,
Okay, sir.
network B also has the same structure as network A. The elements all are different, but it has the same structure. So we replace it like this. These nodes, A is replaced by A prime, B is replaced by B dash, C is replaced by C dash, etc. Even this V1 is replaced by V1 dash, I1 is replaced by I1 dash. Like that we have formed the circuit. We have formed a graph. Okay. Any confusion to this? No. So I'll proceed. So there's a sort of proof of this Tellegen's theorem. There's a Tellegen's theorem. There's a proof of that. And according to that theorem, what it says is, if we multiply the voltage V1 into the current flowing through the other graph, I1 dash, similarly V2 into I2 dash, V3 into I3 dash, V4 into I4 dash, V5 into I5 dash, V6 into I6 dash. If we multiply and add them, the resultant has to be 0. Okay, the resultant of that has to be 0. There's a proof, and this proof is known as Tellegen's theorem. So, is there any confusion in this?
Okay, sir. It means we will apply this theorem with two networks simultaneously.
Yeah. There are two networks and we apply it. Okay.
Okay.
Yeah. But they must have the same structure.
Mm-hmm.
So this is Tellegen's theorem. Now we will understand two-port network. So do you know what is a two-port network?
Yes, sir.
What is it?
Two-port network is a network which has two port. One is a end, one is a receiving port, and second is a end, a sending port.
अच्छा. Okay. बस उतना ही मालूम. Okay. So we will consider this two-port network is here, and there are some sort of passive elements, some sort of impedances are there. There is no voltage source or no current source inside this box. All right. It's only just some resistors, inductors, capacitors, nothing else. No voltage source or current source. So this is port 1, this is port 2. Huh? So what do is, we will consider some current V1 over here, like a voltage V1 is applied here, and some current I1 flows. Similarly, a voltage source V2 over here and a current I2 flows. Okay. Then we can also consider, if we apply V1 dash, then current flowing is I1 dash. If we apply V2 dash, the current flowing will be I2 dash. Then what they do is they apply Tellegen's theorem. Tellegen's theorem which we studied. So this V1 into this I1 dash minus of I1 dash. Because in Tellegen theorem, I1 it should actually be flowing like this. but it is flowing in the opposite direction. So we take V1 into minus I1 dash. Similarly, plus V2 into I2 dash should have been actually flowing in this direction, but it's the opposite direction. So V2 into minus I2 dash plus summation of like the sum of K into Vk, like some voltages, like there's some nodes, okay? Like there are K number of passive elements. So the voltage across those elements into the current flowing through those elements in this network. We will consider that. Similarly, V2 dash into the current flowing minus of I2 plus V1 dash into minus of I1 plus summation of K Vk dash, voltages in this network into Ik, the currents in this network. But we know the voltage in this network is just Ik into Zk. Similarly, the voltages in this network is Ik dash into some Zk. So we write it in this format. When we substitute Vk and Vk dash in this equation, we get it to be like this. V1 into minus I1 dash plus V2 into minus I2 dash plus summation K Zk into Ik dash, which is equal to V2 dash into minus I2 plus V1 dash into minus I1 plus summation of K Zk into Ik dash into Ik. So effectively we get V1 into minus I1 dash plus V2 into minus I2 dash is equal to V2 dash into minus I2 plus V1 dash into minus I1. So usually in the sums, when we have to apply Tellegen theorem, it comes in this format, not the entire one. So it is actually V1 into I1 dash plus V2 into I2 dash is equal to V2 dash into I2 plus V1 dash into minus I1. We just multiply this equation by minus 1. All right. So any doubts in this?
No, sir.
No. Okay. So are you able to see my screen?
Yes, sir.
Okay. So, okay. So we finally get this equation V1 into I1 dash plus V2 into I2 dash is equal to V2 dash into I2 plus V1 dash into I1. All right. Now, so we will consider this network. Same. We apply V1 over here and we short the other port. When we short the other port, what happens? Like consider this is V1 is here, current I1 is here, I2 is here. We short it. So what will be the voltage V2?
0.
Oh, it will be 0. Okay. So what will happen? This V2 will be 0. So it will be V1 into I1 dash. Okay. Then what do? We will do the opposite. We'll apply voltage V2 dash over here and V1 dash will be 0. I1 dash will be something and I2 dash will be something. So what exactly is happening is the original equation was like this. V1 into I1 dash plus V2 into I2 dash is equal to V1 dash into I1 plus V2 dash into into I2. Okay. Now what we have proved, V2 is equal to 0. Similarly, V1 dash is equal to 0. So we get V1 into I1 dash plus 0 is equal to 0 plus V2 dash into I2. Okay. So I1 dash upon V2 dash is equal to I2 upon V1. Is this understood?
Yes, sir.
Yeah. So what we put, we have excited it by V1 and the response was I2. We have excited this by V2 dash, response was I1 dash. So response was I2, excitation is V1. Similarly, for this network, excitation is V2 dash, response is I1 dash. We have written this I1 dash upon V2. Then we have applied Tellegen's theorem. And finally, we get I2 upon V1 is equal to I1 dash upon V2 dash, which we have also proved over here. Okay, so that's why the effect is reciprocal. Like, agar yahan se we apply from here, we get output over here. We apply from here, we get output over here. And the ratio remains constant. So that means the network is reciprocal. All right.
What? I don't understand what you want to say.
अच्छा मतलब अगर एक यहाँ से कुछ एक्साइटेशन डाला तो रेस्पॉन्स कुछ आता है वो जो रेशियो वो है I2 upon V1. ओके सिमिलरली भी यहाँ से ये फिर हम दूसरा पोर्ट से डाल रहे हैं V2 डैश. ठीक है फिर रेस्पॉन्स आता है I1 डैश. तो रेस्पॉन्स एक्साइटेशन इज इक्वल टू I1 डैश अपॉन V2 डैश. हाँ फिर हम लोग ने ये टेलीजेंस थ्योरम का प्रूफ है सब डाला उसमें और मिला कि I2 upon V1 is equal to I1 dash upon V2 dash. मतलब रेस्पॉन्स एक्साइटेशन पहली बार is equal to response upon excitation for second time as well. तो वो रेशियो फिक्स्ड है. हाँ मतलब अगर आप यहाँ से भी लगाएंगे या तो यहाँ से भी लगाएंगे रेस्पॉन्स जो आउटपुट आता है वो रेशियो में आ जाता है. हाँ अगर आप सेम लगाओगे तो सेम आ जाएगा. तो इसलिए बोलते हैं कि द नेटवर्क इज रेसिप्रोकल.
ओके सर.
फिर वैसा ओपन सर्किट का भी वैसे ही फंडा है and this similar thing can be considered and they have also proved it what they have got V2 upon I1 and if the input is this I1 and V2 is the output so V2 upon I1 is equal to V1 dash upon I2 dash. This is the output over here, this is the input over here, so that is also the same. So if whether we open circuit or short circuit the response is reciprocal. All right. So this
ओके सर. ओके.
क्या क्या?
Okay, sir. Yes, sir. I understood.
Wow.
But sir, in general, where we use two-port network?
Where we use two-port network in general. So, yeah, this is a good question. We saw some in the time we use it.
Where?
See, like, we can consider like there's some sort of black box, like, I'll just draw. This is a two-port network. Okay. This is one dash, 2 and 2 dash. Okay. Now we don't know what is inside this network. We have no idea what is there inside it. So what we will do, we
Yes, sir.
will apply some voltage V1, then some current I1 will flow, Then we will measure some voltage V2. Current I2 will be equal to 0. Something like that. So what we will do, we'll apply some voltage, some excitation we will apply. We will see the response and we will assume there, we will do that. Once we do that, what we will get is some parameters. There's something known as some ABCD parameters of the two-port network. So once we get those parameters of the network, we can use that to analyze the response of the network for other outputs, for other inputs and other stuff. All right. Yeah. So we originally didn't know what was there inside the two-port network, but using these concepts, we found certain constants which will help us to determine the behavior of the two-port network.
Okay.
Yeah.
Yes, sir.
Now we will go to week 7, assignment 7. Okay. So calculator है?
Yes, sir.
You're from which college?
Prestige,
From where?
Indore, MP.
Oh, you had joined earlier, na? Then you stopped joining.
Yes. I have some fever, so I attended some classes.
You had fever, so you attended classes.
Not attended. Some.
Okay. What, Corona?
No. Corona has gone.
Okay, okay. All right. So we will answer this question. Okay, there's this network is there. It is open circuit. All right. So the open circuit voltage between A and B is given by this form. VAB is equal to 10 into 1 minus e to the power minus t upon 2 into u of t. All right. So this is the expression of the voltage in time domain. Now we short over here. We directly connect A and B. That time the current IAB is 4 into u of t. What is this u of t? Do you know?
Yes, sir.
What?
UT is a impulse function, not impulse, unit step function.
Okay, unit step function. Okay. So, find the Laplace transform of VAB.
VAB. इसका क्या होगा? 10 by S minus 10 1 upon 1 upon S plus 1 by 2.
Okay. You sure?
Yes, I think.
We're not sure. Okay, so as you said, VAB of S is equal to 10 upon S minus 10 upon S plus half. Okay. We'll simplify it. We will write it as 10 is common. 1 upon S minus 1 upon S plus half. So find what will be the resultant equation.
Equation.
मतलब you simplify this, ना? What is the final equation?
Okay. Ten by s, 10 by 2s square plus s. 10 upon 2s square plus s.
2s square.
Yes.
नहीं.
When we take what I say,
You're almost correct. You missed something. No, you're correct. You're correct. I've actually done the other way. So you have got 10 upon 2s square plus s. What I have done is I've divided by 2. So y is 5 upon s square plus s by 2 I got. Okay.
okay.
So we can write it further as this. We write it as VAB upon s is equal to 5 upon s into s plus half. Alright. Now we have been given IAB of t is equal to 4 into u of t. Okay.
This is given.
Yeah, given. So what is IAB of s?
4ys.
Okay. So IAB of s is equal to 4 upon s. Alright.
8.33. Just my result has come of third sem.
Oh, great.
But they are sent in my mobile number through the message.
Okay, so
8.33 CGPA. I got.
congratulations.
Thank you, sir.
CGPA or semester performance? This which one?
Because in my university CGPA are the main.
For complete.
What?
The CGPA is for the complete thing.
Yes, sir. Because total CGPA is 10. And I got 8.33.
Okay, fine. Okay. Okay. Just read this question once.
What, sir?
Read the question completely.
Okay. If the terminal AB are sorted, then the short circuit current is 1. RAB 2 ohm is connected between terminal A and B. The current from A to B RAB become from this. Using Thevenin's theorem in Laplace domain, find the value of constant AB and tau. All times are in second.
Okay. So how do you solve this?
I do. What?
No, what steps you will follow now? They have told you to do Thevenin's theorem. So what have they given you?
using Thevenin's theorem.
Hmm.
Thevenin's theorem says that consider one source at a time and replace other source by their internal resistance.
Okay.
First of all, we take this voltage source VOUT,
Hmm.
and
And
but there only one source is right.
yeah.
So we no need to sorted anything whatever.
No. So actually, what they have told is they have given you the open circuit voltage, which is VAB. That is Thevenin. Okay.
Yes, sir.
And they have given you the short circuit current. Now the short circuit current is IAB. So you need to find Z Thevenin. We have been given, we have found
Yes, sir. Z Thevenin is equal to VTH upon ISC.
so Z Thevenin is VTH upon ISC. Okay. That is pi upon S into S plus half 4 by S. That is equal to 5 by 4 into S plus half. That is equal to 1.25 upon S plus half. Any doubts in this?
No, sir.
So B plus minus V Thevenin into Z Thevenin. Okay. This is A, this is B. Alright. So the entire circuit is replaced by this form.
Yes, sir.
Okay. Then they are saying they connect a resistor of 2 ohm across AB. They want you to find the current flowing. So what will be the equation of the current?
I is equal to VTH upon ZTS plus 2.
VTH upon ZTH plus 2. What is VTH?
VTS is they are given 5 upon S plus no, 5 upon S bracket S plus 1 by 2.
Okay. What is ZTH?
And ZTS is 1.25 upon S plus 1 by 2.
Okay. This is plus 2 over here. Okay. So we write it as I equal to 5 upon S into S plus half into 1.25 plus 2S plus 1 into S plus half. Is there any doubt in this step?
No, sir.
So this S plus half gets cancelled. So it becomes 5 upon S into 2S plus 2.25.
Yes, sir. 5
This S comes down now.
yes,
This
sir. Yes,
becomes
sir.
plus 2.25. Okay.
Yes, yes.
So this becomes 5 upon 2, you take common out. So 5 upon 2 into S plus 1.125. Any doubts in this?
No, sir. No, sir.
Okay. Now, how will you find I? Like, it will be I is equal to 5 upon 2 into 1 upon S minus 1 upon S plus 1.25 into 1 upon 1.25. Did you understand this?
No.
No.
Yes.
Oh, this will be
5
1.
by
Okay. Let me drop it. this actually is I equal to 2.5. Okay, 5 by 2 is 2.5 divided by s into s plus 1.125 is actually 9 upon 8. Okay. Now we have to do partial fractions and get rid of this form a upon s plus b upon s plus 9 upon 8. इतना ठीक है? So what do we get? 2.5 is equal to a into s plus 9 upon 8 plus b into s. Okay. So s into a plus b plus 9 by 8a. This is fine.
Yes, sir.
So equating the terms, we get 2.5 is equal to 9 upon 8a and a plus b is equal to 0. Any doubts in this?
The s a plus b.
Ah,
as plus 9 by 8 plus bs. But sir, अच्छा okay, अच्छा. We take common s है ना?
s common, s common.
Okay. But we can directly put the value of s is equal to minus 9 by 8, then they can cancel to each other. Then we can find the value of b.
Sorry?
Without taking the common s, we can directly find the value of a and b also.
How?
Put the value of s to minus 9 by 8, then the a will be.
Okay, that also is a method. But this also is same only, give same value. Okay. So
Okay.
this becomes 5 by 2 is equal to 9 upon 8a, or a is equal to 5 into 2, 5 into 8, or 9 into 2. That is equal to 20 upon 9. Is this fine?
What, sir? Because call has come, so I don't.
Okay. So we solved it and we found the values of a and b. Okay. A is 20 upon 9, b is minus 20 upon 9. So the equation of I is 20 upon 9 into 1 minus 1 upon s plus 8 upon 9. We take the Laplace transform, we get 20 upon 9 into 1 minus e raised to minus 8 upon 9, e raised to minus t upon tau. No. It will be 8 upon 9. 8 upon 9. Okay, into u of t. Right?
Okay, sir.
So that's how a is 20 upon 9, b is minus 20 upon 9, and t upon tau will be 9 upon 8.
Yes, sir.
Okay. Yeah. Now we'll proceed with the next question. This is the question. This v1 t is 10 into u of t is applied to this port, and this terminal is shorted. So v2 of t is 0. Then, and the values of the current I11 of t and I12 of t is given over here. Then we connect a 2 ohm resistor over here, and we apply a voltage source plus minus v2 of t over here. Then we will get a current I21 of t over here, and this current also some value we don't know. Now we want to find out this current I21 of t. So we have to use Tellegen's theorem in Laplace domain to find the values of the constant a, b, and alpha. when I21 of t is in this format. Okay, इसमें कोई doubt है?
No sir, doubt नहीं है because I don't know what is says Tellegen theorem.
अभी तो सिखाया था ना भाई.
हाँ, I11 multiply with V2 dash.
हाँ, वही
मतलब
वाला.
जो बैलेंसिंग वाला सिस्टम है ना, पावर बैलेंसिंग.
क्या क्या?
पावर बैलेंसिंग वाला फंडा है शायद.
पावर बैलेंसिंग फंडा एग्जैक्टली नहीं है उधर. वो तो केवीएल केसीएल का कुछ फंडा है. ओके, सेम ग्राफ होने की वजह से वैसा. ओके, so what we will do is we will write down v1 of s, I11 of s, I12 of s in s domain. v1 of s in s domain is what?
10 by s.
Okay, and I11 of s and I12 of s is what?
I11 s is equal to 5 1 upon s plus 8 and I2 is 1 upon s plus 8.
Yeah. Okay, so we write down what is I11 of s? 5 upon s plus 8. I12 of s is 1 upon s plus 8. Okay, now we also know v2 of s, v2 of t is 8 into e minus t. So what is v2 of s?
1 upon 1 plus s. S plus 1, you can say 1 upon s plus 1. नहीं, 8 upon s plus 1. 8 upon s plus 1.
So v2 of s is equal to 8 upon s plus 1. So also across over here there's a 2 ohm resistor and the current is flowing in this direction. So what will be the voltage across this one?
I21 multiplied by 2.
Yeah. So in Laplace domain will be 2 into I21 of s.
I21 upon s is a 2 upon s bracket 2 upon s square plus 8s.
No. It is just 2 into
2
I21 of s. That's all.
Okay, it means 2 upon s plus 8.
What is I21 of s? This is I12 of s. This is I21 of s. अलग है.
Okay.
So now we will apply Tellegen's theorem. We apply Tellegen's theorem, it will be v1 of s into minus of I21 of s. Is that fine? No, but
Yes, sir.
I21 of s should have been in this direction. It is going in this direction, so it is positive only. So it will be v1 of s into I21 of s. Okay. Plus this voltage is 0. This voltage is 0 into this current. We have not been given the value. So it will be plus 0 into something. So that is 0. So v1 of s into I21 of s plus 0 is equal to this voltage. This voltage is 2 into I21 of s. Okay.
Yes, sir.
That will be 2 into I21 of s into this current, and because it's going in this direction, so minus sign. So this will be into minus of I11 of s plus this V2 of S into I12 of S. Now, if I12 of S was in this direction, we have to consider minus sign. But since it is in this direction, we consider positive sign. So it will be V2 of S into I12 of S. So any doubts still here?
Sir, please tell me again in sign convention.
If the current is flowing into, then it will be minus. If the current is flowing out, it will be plus.
Okay, it means out plus in minus.
Ah.
Okay.
Okay, so we got it in this form. Now we substitute those values. So it becomes 10 upon S into I21 of S is equal to minus 2 I21 of S. 2 I11 of S is 5 upon S plus 8 plus V2 of S is 8 upon S plus 1 into 1 upon S plus 8. Okay. Now we take I21 of S common. So it will become I21 of S into 10 of S plus 10 upon S plus 8 is equal to 8 upon S plus 1 into 1 upon S plus 8. So any doubts in this?
No, sir.
So we take 10 common. I21 of S into 10 into 1 upon S plus 1 upon S plus 8. 8 upon S plus 1 into 1 upon S plus 8. Okay. So you get it as I21 of S into 10 into S plus 8 into S plus 8 is equal to 8 upon S plus 1 into 1 upon S plus 8. This S plus 8 and this S plus 8 get cancelled. So I21 of S is equal to 8 upon S plus 1 into S upon 10 into 2S plus 8. Any doubts in this?
No, sir.
Wow. So we get it as I21 of S is equal to 0.4 S upon S plus 1 into S plus 4. Any doubts in this?
No.
So this will be 0.4 into S upon S plus 1 into S plus 4. That is 0.4 into A upon S plus 1 plus B upon S plus 4. All right. So we have find a partial fraction of this S into S plus 1 into S plus 4 is A upon S plus 1 plus B upon S plus 4. So S is equal to A into S plus 4 plus B into S plus 1. So we get S is equal to S into A plus B plus 4A plus B. Now we equate the coefficients of S and constant. So we get A plus B is equal to 1 and 4A plus B is equal to 0. Okay. Now, if we solve it, we will get A to be equal to minus 1 by 3, B to be equal to 4 by 3. So we will substitute over here. So we get I21 of S is equal to 0.4 into minus 1 by 3 into S plus 1 plus 4 by 3 into S plus 4. Okay. So we get I21 of t, when we take the inverse Laplace transform, we get it to be of this form, minus 0.13 e to the power minus t plus 0.533 e to the power minus 4t into U of t. Okay.
Okay.
So we have got it in the required form. A is minus 0.133. B is 0.533. And alpha, which we want, is equal to 4. Okay.
Yes, sir.
Any doubt in this? No.
No, sir.
Okay. What about Mohammad Murshid? Any doubts? Any queries? Okay. So we will continue with the next sum. In this sum, what they're asking, there's this network over here. Okay. There's a voltage source E1, E2, 7 ohm voltage source, 13 ohm voltage source. I1 was 4 ampere, I2 was 9 ampere. Okay. Now, there's just some resistance R was then, I3 will be 4 plus 9, which is equal to 13. Okay, initially. Then we change this resistance R to 15.45 ohm and we keep all other resistances and EMFs unchanged. Then we have to find the new value of I1, I2 and I3. Okay. So we have to use compensation theorem to solve this problem. So do you remember compensation theorem?
No, sir.
अभी तो प्रूव किया.
हाँ.
हाँ.
नेटवर्क ग्राफ थ्योरी ना?
नहीं वो उसके पहले.
उसके पहले.
अब ज्वाइन
Sir,
किया
I
फिर.
forget it.
Forget it. अरे. अच्छा. Okay. So Deepak Kumar. So now we have to apply compensation theorem. So what actually we do is, as we have told you, this is simplified format. We have initially R was 2 ohm, then R will become 15.45 ohm. So that means first I1 is 4 ampere, I2 is 9 ampere, I3 is 13 ampere. Okay. And R was 2 ohm. Any doubts in this? It's all given in this.
No, sir.
Then R changes to 15.45. So the change in Z, delta Z is equal to 15.45 minus 2. That is 13.45 ohm. Okay.
Sir, we will minus in this.
Because change is the difference, 15.45 minus 2.
Okay, it means currently impedance is 13.45.
No, currently impedance is 15.45. But the change in impedance is 13.45 ohm.
Okay.
Yeah, BZ is 15.45. Z, no. No, it means Z plus delta Z is 15.45 ohm. Okay. Z initially was 2 ohm. So delta Z is 13.45 ohm.
Mm-hmm. Same thing.
Same thing only. Just to teach you. That's why. Okay. And initially the current I3 was 13 ampere. So according to compensation theorem, what happens is these voltage sources are replaced by short circuit. These resistors remain the same. And the new network comes out to be like this. It be this is 7 ohm. This is 13 ohm. This comes out to be plus minus I into delta Z. This will be delta I, and this will be Z plus delta Z. Okay, this is what compensation theorem states.
Okay.
So
This what is the I?
I is the original current,
It will-
which is 2.
In this branch,
No, delta I is the current to the branch. I was the original
okay.
current to the branch. That was I3.
I3.
Ah.
I3 is 13, right?
Oh, okay, sorry. I3 is 13 into 13.45. What is 13 into 13.45?
One 174.85.
That is equal to 174.85. Okay. And what is Z plus delta Z?
15.45.
Very nice. So we write the new network like this. New network can be written as 7, 13, delta I3 because through this branch plus minus 174.85 divided and a resistor of 15.45 ohm. Okay, any doubts in this?
No, sir.
So what is delta I3 then?
Delta I3. Delta I3. Node voltage we don't know.
What we do is this is 7 upon 7 and 13. This is a parallel resistance plus this resistance. Divide by this. We divide 174.85 by that. So delta I3, but delta I3 is in this direction, but the voltage source is in this direction. So it will be delta I3 is equal to minus 174.85 upon 15. Huh?
No, sir. No, sir.
So what is this value? What is 7
What
into?
is this?
What is what?
It will be 91 divided by 20.
What is that?
15. 174. 8.85. 8.74
Sorry?
minus bala.
8.7
Minus 8.7.
25 ampere. Okay. This is a change in I3. Similarly, there is a change delta I1. Similarly, there is a change delta I2. इसमें कोई doubt है?
No, sir.
So change
It
in
means
delta. Huh?
all current will be changed, right?
Yeah, all currents will be changed. No? All currents will be changed. So delta I1 is equal to minus delta I3 because they are in the opposite direction into 13 upon 7 plus 13. By current division rule, you know that, right?
Yes, sir.
So what will be the value?
Minus tel I3.
Delta I1 is how much?
8.7425.
No, okay. It will be in this direction. So delta I1 will be plus delta I3 into 13 upon 7 plus 13. So what do you get it to be?
Minus 5.68.
Yeah. Okay. So similarly, what will delta I2 be equal to?
Five multiplied by 7. Minus 3.059.
Okay. Okay, these are the changes in the currents. But the actual current I1, the new current I1 new is equal to I1 old plus delta I1. Okay,
Okay,
is this
sir.
clear?
Sir, what I1 new is equal to I1 old plus del I1.
Yeah.
Okay, okay.
So I1 old was 4 ampere. Huh?
Yes, sir.
I2 old was 9 ampere.
Yes, sir.
So 4 plus delta I1, how much is it?
Minus 5.68.
68. So what is it? 4 minus 1, 5.68 is how much?
Minus 1.68.
Yes. This is minus 1.68 ampere. Similarly, I2 new is equal to I2 old plus delta I2. So that is how much? I2 old is how much? It is 9. 9 minus 3.059. That is how much?
To 9.
Minus 3.059.
6.059.
9
No,
minus
no.
3.059.
3.0. 5.941.
Yeah, correct. Then I3 new is equal to I3 old plus delta I3. What is I3 old?
13.
Yes. Minus 8.7425. Do this now how much?
4.2575.
Yes, very nice. 4.2575 ampere. Great work. Okay. So you got good answers. Now we will go to the last question.
Sir,
What?
wind up this lecture here.
Why not? Why?
Sir, because calls are coming.
What is coming?
Call of my friends.
So put your phone in silent, huh?
Okay.
What is the big deal here? Even I got calls from my friend. I put it in silent. I told him I'm busy
Oh,
because
oh.
I'm teaching Deepak Kumar. I have to teach him well. Huh? He'll be the
Okay, thank you, Pat.
next topper of NPTEL network analysis. Uh-huh.
No, sir. No.
Why not?
Yes, but
But
I have not registered for the NPTEL exam.
today's the last day.
Yes, sir.
So you can register, no?
No, sir. I will not do.
Oh, cha. Oh, then why are you actually doing this course then?
For learning purpose.
Oh, cha.
Because I am in electrical engineering, so this is the basic thing
Yeah.
or base of engineering.
Yes.
So we have to do this. Otherwise, we can't live in the world.
Okay. Yeah, very correct. Okay. But exam also you can give, no? It is not something you can test yourself how much you've learned. So just my suggestion up to you. Anyway,
Yes.
okay. Yeah. So now we will consider this diagram. These are phasors. You know what are phasors, right?
Mhm.
So,
Phasor.
uh, sorry, you were saying something?
No, sir. No.
Okay, no. So so assume the supply frequency is 50 hertz and all phasors represent RMS values. Usually they represent RMS values. And these are like one phasor is the reference phasor and these are the voltage, the phase shift with respect to some reference phasor. And now we have to find the RMS value of VMN, and then the values of IA, IB, IC. Okay, so we must find VMN, IA, IB, IC. So what we will do is we will first find so in this network there are only two nodes, node M, node N. So we will assume node N to be the reference node and we will apply nodal analysis to solve it fast. If we apply mesh analysis, we have to solve this mesh, this mesh. Instead, we apply nodal analysis, we just have to do KCL for one node. Okay. So we will consider that method. So we will get VMN, voltage over here with respect to N. So we'll assume the currents to be flowing in this direction, okay, outward. So that will be VMN minus this voltage, 200 angle 45 divided by 80 minus j upon 2 pi into 50 into 40 into 10 to the power minus 6. Any doubts in this?
250.
Pi into 50 into 40 into 10 to the power minus 6 because micro.
Okay, sir. Okay.
plus VMN minus this one 200 angle minus 75 upon 40 minus J to 2 pi into 50 into 80 into 10 to the power minus 6. Okay.
Okay, sir.
Plus this current, that is VMN minus 200 angle 165 upon 40 minus J upon 2 pi into 50 into 40 into 10 to the power minus 6 is equal to 0 by applying KCL
Okay, sir.
at node M. So we get it as VMN minus 200 angle 45 divided by 80 minus, what is this? 2 pi into 50 into 40 into 10 to the power minus 6, calculate. कितना है?
Yes, sir. I understood.
What do you understand? I told you to do something. Huh? What I told you to do?
Sir, I I did not listen. I am disturb. I I am disturbing because calls coming.
I told you now. Put your mobile in do not disturb mode.
Yes, now I did put.
Finally.
Do
Finally. So calculate this value. What will this value be?
this
Hmm?
value.
Yeah.
Mm, 2 multiplied by 3.14.
कितना है?
Sir, I don't get it now.
Huh?
I did not get it now.
Why?
You got it?
Yes, I got it.
Well, no. It means you obtained this value, this result.
I wanted the result. That's why I told you to calculate.
Mm-mm.
जल्दी करो, जल्दी जल्दी. Are which
Sir, it
calculator
will
you're
take
using? Which calculator you're using?
scientific.
Sure. Okay, no need. I use this calculator. You have this calculator?
Yes, but different from this.
Yeah. It will be faster, yeah. Otherwise, what is the use? It should be fast. Okay. So this will be J 79.57 plus VMN minus 200 angle minus 75 upon 40 minus J into, it is 39.787 plus,
Hello.
हाँ बोलो.
डू नॉट डिस्टर्ब मोड में भी आवाज नहीं आ रही आपकी.
मेरा आवाज आना चाहिए, बाकी सब आवाज नहीं आना चाहिए।
मतलब उतने टाइम के लिए वो साइलेंट कर देता है।
हाँ, ये so we take 40 minus j 39.787 is half of this. So we multiply this by 2. Okay, these by 2. Then we'll get a common denominator. So we will get Vmn minus 200 angle 45 plus 2 into Vmn minus 200 angle minus 75 plus 2 into Vmn minus 200 angle 165 upon RER 80 minus j into 79.57 is equal to 0. We take this to the right hand side, it multiplies by 0, it becomes 0. So it becomes 5 into Vmn is equal to 200 angle 45 plus 2 into 200 angle minus 75 plus 200 into angle 165. Okay. When we solve this, we will get Vmn to be equal to 40 into angle of minus 135 volt. इसमें कुछ डाउट है?
सर इसमें कैलकुलेशन ही करना है ना?
क्या क्या?
इसमें तो जस्ट कैलकुलेशन करना है बस, और कुछ भी नहीं है।
बस जस्ट कैलकुलेशन ही करना पड़ता है, जो इसमें जिसमें मिस्टेक हो जाता है और मार्क्स कट जाते हैं,
हाँ,
बस उतना ही है। ठीक है।
सर, मैं
आप तो इतना बड़ा स्टूडेंट है, कैलकुलेशन में मिस्टेक ही नहीं करते, तो आपको क्या टेंशन? हाँ, ठीक है। देन IA will be equal to the voltage applied over here minus Vmn divided by the impedance over here. That will be equal to 200 angle 45 minus 40 at an angle minus 135 upon 80 minus j 79.577. When we do this, we get it 2.127 angle 89.8483 ampere. So this is the RMS value which we want. Similarly, we can write ID to be equal to 200 angle 165 minus Vmn. So it is 200 angle 165 minus 40 into angle minus 135 upon 40 minus j into 39.788. So IB comes out to be equal to 3.249 angle minus 161.045 ampere. कुछ डाउट है इसमें?
नो सर।
डाउट नहीं रहेगा ना, अगर सॉल्व नहीं करोगे तो डाउट कैसे आएगा? So IC is equal to 200 angle minus what? Minus 75 minus 40 into angle minus 135 upon 40 minus j 39.78. This comes out to be 3.2489 approximately angle minus 119.2583 ampere. So this is the RMS value, this is the RMS value, and we have solved it. Okay.
सर व्हाट इज फॉर्मूला ऑफ आरएमएस वैल्यू? v maximum by √2?
Yeah, but over here this is just the RMS value.
हाँ, here already given they, so it will come in form of RMS, right?
Yeah, because we have these values were given in terms of RMS value. These were given in terms of the peak value. then we'd have to divide it by root 2. All right.
Okay. Okay.
And so if you'll observe this circuit, it is like a three-phase power supply. All the voltages are equal, 200, 200, 200, but the phase shift between them is not equal. In three-phase power supply, what should be the phase shift between two power supplies?
120.
So between these two, it is 120, but between this and this, it is not 120, and between this and this, it is not 120. And what we ideally want is the phase shift to be 120, the amplitudes to be equal, as well as the load which is connected also should be equal. But if we see over here, these two loads are equal, but this is double of these two loads. Okay.
If this is not equal, and what will happen?
Then unequal currents are flowing. Now, what we found IA to be some amount. We found IA to be 2.12, but IB is 3.24 and IC also is 3.24. But ideally, what we want IA, IB, IC to be have the same value.
Okay. Unbalanced load. This is to be unbalanced load.
Yeah, this is unbalanced load.
Okay. In practical, this is not possible, right?
Practical happens like this only. Load is always unbalanced.
What?
In practical case, load is usually unbalanced only.
Okay, usually an unbalance.
Yeah, but they have some method, some ways they will do to balance it and all that. That is high level stuff, which you will soon learn. You're doing electrical engineering. Which college? I forgot the name of the college.
What?
Your college name is what? I forgot.
I told you so many times.
Shakti College, yeah.
No. Prestige. Prestige is cooker, right?
Okay.
You know?
Yes, I know.
Prestige.
Okay. Congrats. Fine.
That is what.
Okay. Then any other doubts you have?
No, sir. No, not now. But when I will solve, then I will. मतलब तब doubt हो सकता है कुछ.
हाँ, तो इसलिए अब भी सॉल्व करना चाहिए था ताकि अब भी डाउट होता था, क्योंकि यही तो डाउट क्लियरिंग सेशन था. ठीक है. वही. अच्छा, तो अगर कोई डाउट नहीं है तो बंद कर देते मीटिंग. हो गया.
Yes, sir.
Okay then, thank you.
Okay, sir. Good night.
Good night. Bye.